Now, let us just first try to understand the free vibration of such undamped system. And in fact, I will quickly go through this because of the sake of the completeness and because of having a recap over the whole thing. Because already we discussed this part in numerical methods, and there, in fact, we dealt with a 3 degree of freedom system. So this kind of a system is very much known to you. And then if we write the free vibration equation, then we will consider that the force vector F1t and F2t, they are null vector, that means 0 0 vector. And so if I write down both the equation in the matrix form, it will come as M1 0 0 M2, that is the mass matrix, then the acceleration vector, then plus the stiffness matrix. Here you see also the stiffness matrix is symmetric about the diagonal, and then the displacement vector, that is equal to 0 0. Now if you can remember, we talked about the mode shape, and we talked about the fact that any nth degree of freedom system will have n number of natural frequencies, and it will have n mode shape. That means these natural frequency and mode shapes are the likings of these structures. That means if you allow the structure to undergo a free vibration, uh, initially starting with a shape of a particular mode shape, then it will vibrate with that particular, with the particular natural frequency which is associated with that mode shape. That means it's a kind of a general liking. Okay, say I may like to teach, I may like to do research, maybe I also may like to do some consultancy, but there is an order of that. And then if I try to do if I like to carry out research much more intensively, then my first liking is doing research. So if no constraint is kept on me, then possibly I'll try to do more research rather than teaching. So teaching comes in the second position. So that way, if I just try to make a kind of comparison with this dynamic behavior of the system and with the human behavior, then I'd say that, well, research is my first frequency, and what kind of research I'm trying to do. Say somebody wanna do computational research, somebody wanna do experimental research. So that is my mode shape. That means if I like to do computational research, so with my liking of research, the associated form is the computational research. Therefore, so that will be the first mode shape. I mean, and maybe if I try to do teaching also, I mean, if that is my second liking, then maybe that I like to go for offline teaching. Okay, this online teaching doesn't appear to me very much exciting to me. So so that means the second natural frequency for me will be teaching, and the corresponding shape is the offline mode. So the same thing is true for the structure. Sometimes I wonder that how similar the behavior of a human being and a structure is. Uh, in fact, if you just keep it thinking on this way, you will have a different kind of feeling and a philosophical development in your mind. In fact, you know, see, the living beings, they can be called as animate, and the behavior of an animate is actually consists of a combination of behavior of the non-animates. I mean, if you see that each and every part of our body, they are actually being controlled by the the systems which are really non-animate. For example, you see our heart is breathing and then the bloods are flowing. These are completely a part of the fluid mechanics, and the people are very heavily doing research on it. One of my friend in University of Manchester, he's doing research that we are having nowadays. I think you people use Omron uh, blood pressure measuring machine, then that is not very much accurate. So how we can have much more accurate blood pressure measuring machine? So the boundary between the various disciplines are now disappearing. So everything is science and engineering, and we have to think of an interdisciplinary form, so that because the problems which are coming, they are not thinking that, well, I am a problem of physics, or I am a problem of chemistry, or I am a problem of engineering. A problem is a problem, and that might have different aspect. In reality, that is what happens. And therefore there is an amalgamation of the knowledge of the different people from different sides. For example, say if you go on if you try to make some research on missile, you have to think a lot about the structures, because how the missile structure will vibrate, how it will not collapse in between, how much temperature it has to withstand while moving with a very high velocity. Nowadays, we talk about the hypersonic missile. Hypersonic missile means the velocity is more than a supersonic missile, and if the velocity of the supersonic missile is Mach, then it's a around 4-5 Mach, then we call it beyond 4 Mach, we call it hypersonic. So that way all the problems are fixed, and we always think about, I mean, we should always think about the physics of the problem, and then to solve different part of the physics of the problem, we really need some kind of a uh, a comparison with various system, and that's why a dynamically vibrating system I try to compare with the attitude of a human being, and these are being a very fruitful thing. For example, nowadays the people are solving many mathematical problem using neural network. Okay, what neural network is? How the neuron passes the very feeble current through our nervous system to the different limbs, so that we can move our limbs according to our will. So this is basically the neural network, and with this, the way a human body solves the problem using the neurons, if we can use the same kind of algorithm for solving a problem of engineering, say structural engineering, then we'll say that it's an application of neural network in the domain of structural engineering. So similarly, like, so we can say that these natural frequency and the associated mode shapes are likings, the natural likings of a structure. And then when the force acts on it, then this natural liking and the force, they negotiate, and they then reach somewhere which is neither exactly the natural features, nor exactly the external one which is imposed on it. It is something in between. I mean, you can understand, and then we can mathematically try to calculate, understanding that these features. Like, say somebody want to create some pressure on me, then maybe I will try to initially resist, and then maybe that there will be a negotiation, and maybe that I will also get deviated from uh, some of my features a little bit, and the other person will deviate also from his demand a little bit, and then there will be a negotiation, and something will come out. So it is like that. Now we are only talking about the features of the structure, but whenever, and that's why we are talking about the free vibration, because we are interested to find out the features of the structure, which are natural frequency and the mode shapes. And that's how with the right hand side we have made the forces at 0, and we are giving some initial condition, and then we are not applying any force, we are just giving some initial deformation or velocity, and then we are releasing, then the structure keeps on vibrating. Now we have to see that what are the, from these consideration of the free vibration, we have to pick up the features of the structures, which are natural frequencies and mode shapes. And how many natural frequencies and mode shapes we'll have, that will be equal to the number of degrees of freedom of the structure. So if x1t and x2t are the solution, then say alpha x1t and alpha x2t also represent a solution, because if you have a solution and if you just multiply that by a scalar quantity, then also that will be a solution, where alpha is an arbitrary constant. You can remember that we told that when we talk about a natural frequency and the mode shape, then it is a shape. Now the shape may have, depending on the initial condition, the shape may have different amplitude. Say if I take a bent shapes, then maintaining that shape, the each point may deform more or each point may deform less, but the ratio of the deformation of each point will remain same. So that shape is called the natural, associated with the natural frequency of the system or the structures, and that is called the mode shape. So we are here, when we are talking about natural frequency and the mode shape, we are not rather talking about any particular number of numbers indicating the displacement. Rather, we are talking about a shape. Okay, so that the ratio of the displacement of various points remain the same. So this means that x1t will be some u1 into ft, and x2t will be equal to some u2 into ft. So u1 is mm, uh, for the participation of the shape, and ft is the same time function. That means uh, ft will denote how with time the shape is changing, but the shape itself is remaining as same. Only its magnitude of all the points are increasing simultaneously, so the shape is being maintained, or it is decreasing simultaneously, so the shape is being maintained. So, and this is called the modal vibration. That means the vibration maintaining a particular mode and the corresponding, automatically if a system vibrates in a particular mode, then its natural it will vibrate in the corresponding natural frequency. So if we substitute that x1 equal to u1 ft and x2 equal to u2 ft, then we get this equation. You see, this is the similar type of things we learned while talking about the eigenvalue problem. And so here also we'll have the eigenvalue problem. And we took an example of 3 degree of freedom system. Here we are taking the example of the simplest one, 2 degree of freedom system, because we will discuss many other things which will be easier to understand with 2 degree of freedom system. So we get that m1 u1 f double dot t plus k1 1 u1 plus k1 2 u2 into ft equal to 0, and then m2 u2 f double dot t plus k1 2 u1 plus k2 2 u2 into ft equal to 0. Now the whole problem with these two sets of differential equation lies in the fact that both the equations are coupled. What is meant by coupled equation? By coupled equation, you see, it means that in the first equation, u1 is present and u2 is also present. Okay. Similarly, in the second equation, also u1 and u2 are present. That means there is a coupling. Coupling means it's a relationship. So that means if you create a displacement in U1, so that will have an effect at U2 and vice versa. So if we try to solve the problem, and that's why you see, if this in the first equation, if this k1 to u2 term would not have been there, only if this would have been, then the equation would have been expressed in the in terms of only u1, then possibly we could have solved it as a differential equation, as we have done for single degree of freedom system. But here that doesn't hold good. Therefore, what happens that the first equation can be written as minus f double dot t over ft. You see, if I just from this equation, if I consider the first equation, if I try to find out what is the value of f double dot t by ft, that means, other way speaking, if I try to separate the variables, so if I try to keep the the terms involving time variable on the left hand side, and the terms involving the space variables on the right hand side, then we get this. You see, in the right hand side, we get this k11 u1 plus k12 u2 equal to m11 u1. Or from the second equation, we get, if we express it, it will get this. Now, both of these will be constant. If these equations are to be satisfied, then the only way, you see, T is changing independently. U1 and U2 are not having any relationship with the change of T. Therefore, the only possibility that the equation can be satisfied is that the change of T takes place in such a way that the ratio of f double dot T and ft, and the ratio of the space variables, the terms involved in the space variables, they remain constant. Individually, maybe f double dot T is changing, ft is changing, but the ratio is being maintained as constant. And so we are considering that constant equal to lambda, and therefore we can further write that f double dot plus lambda into ft equal to 0. And now it looks like the differential equation of a single degree of freedom system in the undamped condition under free vibration. And once we write that, then what we can do is, instead of f double dot t, we can substitute minus lambda ft. So we may again rewrite the equation k11 minus lambda m1 into u1 plus k12 into u2 equal to 0, and k12 u1 plus k22 minus lambda m2 into u2 equal to 0. This is now, if we can proceed further, and if we wanna have a solution for ft, then for this kind of a differential equation, we already discussed that the solution, since you know that if this expression has to be 0, then upon taking double derivative, it has to be expressed in the same form that of ft. Otherwise, they cannot cancel each other. That means their summation cannot be 0. That means it should be such a function that its form doesn't change due to successive differentiation. So that is only possible if it is an exponential function, because if you differentiate exponential function, then the same est will be there, the other constant terms will come out. Or it may be harmonic, that means it may be sine, cosine, etc. But the point is that whenever we use an exponential function, say e to the power x, we know that we are covering the harmonic function also, because e to the power I theta, we know that e to the power I theta equal to cos theta plus I sin theta. That means if the solution really doesn't contain, say, both the terms cos and sine, then automatically, say, the imaginary part that will come as 0, the constant related to the imaginary part will come as 0, and then automatically we'll have a solution in terms of sine terms, or maybe we can later on convert it to cosine terms by making a phase difference. So we take an exponential form of the solution, and because that covers both the harmonic function as well as the exponential function as well as the hyperbolic function, and these are the three functions which may repeat itself upon successive differentiation. So substituting a into e to the power st, which is a more generalized form because which encompasses these three types of solution together, we get s square a into e to the power st plus lambda a into e to the power st equal to 0, and where s equal to plus minus of square root of minus lambda. And then naturally you know that if we have 2, 3 solutions, then the general solution can be a summation of both of them, because summation of all the solution multiplied with any coefficient, because if these separately satisfy the equation, then, and if this also separately satisfy the equation, so their summation will also satisfy the equation. So therefore more generalized form will be to take their summation with some coefficient, and then so we can write it further that a1 e to the power minus lambda t plus a2 e to the power minus lambda t. Now there is a possibility that lambda can be negative or lambda can be positive. So if lambda is negative, then a1 e to the power plus square root of minus lambda t, that will tend to infinity, and a2 e to the power minus of minus lambda t, that will tend to 0. So the solution will be not defined mathematically. Okay, we cannot express the solution. So, but since we are working with a physical problem and a physical vibration problem we are focusing on, therefore in a physical vibration problem neither the solution can be infinity and nor the solution can be 0. Therefore we are disregarding the fact that lambda can be negative. So for the correct solution, lambda should be positive. In fact, the solution of the differential equation, when we are considering it mathematically, it gives with the arbitrary constants involved, it gives a large family of solutions. Okay, depending where you keep on changing the value of the arbitrary constants, and you will get one after other, solutions, and you can, that way you can have a large number, possibly infinite number of solutions. They are put in the umbrella, one same umbrella, and you can say that the solution within this umbrella, each of the solution within this umbrella is a solution to the differential equation. Then the solution which is particularly applicable for the physical problem we are considering, for that you have to see that whether the solution is properly giving the physical meaning to the problem what you are choosing. And while doing so, here we see that lambda cannot be negative. Hence, we consider lambda positive only, and then we can write lambda equal to omega square, because otherwise minus lambda equal to, we could not write that some quantity square. So we get it ft equal to a1 e to the power I omega t plus a2 into e to the power minus I omega t. That means again we are just adding up the solutions. Now you see, if I work out, that means if e to the power I omega t, if I write it cos omega t plus I sin omega t. Again, e to the power minus I omega t, I may write that cos omega t minus I sin omega t. And if we substitute it here, then we'll have a1 plus a2 cos omega t plus I into a1 minus a2 sin omega t. Now the problem is that since we are discussing about the solution of a physical problem, therefore we cannot have imaginary solution. We cannot have an imaginary part in the solution. So that means a1 and a2 can have any value. So out of that, again, considering the physical nature of the problem, from a large umbrella, we have to narrow down to some cases such that ft cannot be imaginary. It will always be non-imaginary or real. So can you tell me that what is the condition which may be put on A1 and A2 such that this solution become real? Okay, now if you have paper in front of you, you can just work with that if I consider A1 equal to C plus ID and A2 equal to C minus ID, then what values we get for A1 plus A2 and I into A1 minus A2. Can you please try to calculate where C and D are not imaginary, they are real? Can you calculate that? That means if we have to impose an extra condition on A1 plus A2 from the large family, or maybe there is a large bucket which is full of solutions, we are picking up some particular cases where A1 and A2 are complex conjugates, and in that case what will happen is that A1 plus A2 and I into A1 minus A2 both will be real. So now we are moving with the assumption that A1 and A2 are both complex conjugate. Then the requirement that ft will be a real function is satisfied. So here is the concept. I mean, in most of the book, people just show it here and then they just show the steps and then they directly go to the solution. But you should understand, I believe, I mean, you will enjoy having the understanding behind this mathematics. Otherwise, this mathematics will appear to you a very dry thing. So the solution we considered was x1 t equal to u1 ft, x2 t equal to u2 ft, and then the time dependence is harmonic, and a1 a2 equal to we may consider as c cos phi, and a1 minus a2 equal to c sin phi. Say that means you are telling 2c and minus 2d. So 2c is equal to cos phi and minus 2d equal to c sin phi. So we can, I mean, we can get a value of c, that means c square. If we take the square of these two things, that means a1 plus a2 whole square, a1 minus a2 whole square, then we will get it c square. That means, so that way we can adjust the value of c so that a1 plus a2 can be expressed in the form of c cos phi, and a1 minus a2 can be expressed in the form of c sin phi. And then when we are dealing with cos phi and sin phi, and then there are another cos term which was present beforehand. So therefore it is a cos term in one case, and in another case sin term. Therefore we can just write it as c cos omega t minus phi. So now we can write down, that means instead of lambda, by substituting omega square, because we are considering a case where lambda is positive, and we get k11 minus omega square m1 into u1 plus k1 to u2 equal to 0, and then k1 to u1 plus k22 minus omega square m2 into u2 equal to 0. So this is the form that you see. That means when you write it in the matrix form, then k11 minus something, and then k12, then k12, and then k22 minus the same thing into u1, u2. So this form is called an eigenvalue problem. You see that normally if you wanna solve it, then from both the equations you will get u1 equal to 0 and u2 equal to 0. But as we discussed about the fact that there can be three, if there is a set of simultaneous equations, there can be, and if we use Cramer's rule, so the unknown quantities will be d1 by d, and then d2 by d, and d3 by d. But they will have unique solution if all d1, d2, d3, and d are non-zero. They will have no solution if d1, d2, d3, and d are 0, and because then the 0 by 0 is undefined, so no solution. And they will have infinitely many solutions if only d equal to 0, but d1, d2, d3 are non-zero. Okay. Sorry, I mean, I'm just telling the opposite thing. That means if d1, d2, d3 and d equal to 0, then we'll have infinitely many solutions. And then if d1, d2, d3 are non-zero but d equal to 0, then we'll have no solution. Because it is coming as an infinite form, and then we really do not know what is the meaning of infinity. So it is having no solution. Now, in here, we cannot have a zero solution because we are talking about a vibration problem. So if U1, U2 are both 0, that means the system is in the static condition, no vibration is taking place. But we are interested, so that is a possibility. But again, we are just discarding that possibility. We are thinking about the possibility that there should be a non-zero solution, because a vibrating system means the displacement is taking place. So we pick up the situation of infinitely many solutions. That means neither we can have unique solution, because unique solution is a trivial solution, zero solution, nor we can have no solution. Therefore, we have to pick up the solution where U1, U2 are non-zero, and so there is no way other than choosing infinitely many solutions. And when there is an infinitely many solution, then only it comes that the ratio between the two variables is same, remains same. That means the shape remains same, but if they are multiplied by any constant, then each one of them will be a solution, and that way there can be infinite number of solutions. So it will only be possible that this infinitely many solution only occurs if the determinant of this matrix is 0, and then it becomes a polynomial of the second order in omega square. So yes, there is a mistake here. It has become W. And this equation is called characteristic equations. So let us end up today here up to the characteristic equation, and then we will continue our discussion in the next class.